Good afternoon, students. Am I audible?
Yes, sir.
Okay, fine. Let me share the screen. I hope you are able to see my screen. Okay, good. So let me start. Yeah. So in the last class, we were looking at what is there in the social network analysis. What are the contents that we are going to cover? What kind of evaluation that we will be doing? And we also looked at the motivation to study this. We looked at some of the necessities to look into these kind of analysis. So for that, we took some case studies and then explained. So all these case studies are explained in Barabasi. So if you want to have more details, please have a look at the Barabasi's book on network science. All the books are some of the content which are required for these lectures are uploaded in this Piazza, so you can have a look at it. And the network science book is completely available online. So that link is also shared in Piazza. You can have a look at it. So you can read it online actually. So for today's class, what we are going to look at is some of the basic graph theory concepts that might be necessary for the further understanding of this social network. Because when we are looking at the social network, what are we going to look at is a graph in a very large scale. Okay, so social network analysis means you are going to look at a graph, which sometimes we call it as a network also, right? So network and graphs we will they mean the same thing actually in our course at least. Okay, so the graph that we are going to look at, especially in the social network analysis, is going to be a very huge graph. Okay, so the number of nodes will be many, and the number of edges also will be many, and there might be some occasions in which the number of edges might be very sparse, but always the number of nodes will be very heavy. Okay, very many. So to understand the concept well, so this class we will be concentrating on a little bit on the basic graph theory concepts. So the basic graph theory itself is a separate topic actually, right? So we will not be going into look at all the concepts in the graph theory. What we will be looking at is to some basic concepts that might be necessary for understanding the social network. What are the problems, or what are the issues? What are the characterizations that we can get from the basic graph theory course to the network? Okay, so there are basic differences when we are looking at the basic graph theory course and the social network. Okay, so I will be spelling it out when the course moves on. Okay, so let's see that in the course of explaining the concepts in social network. Okay, so let's start that basic graph theory concepts. Okay, so graph theory, as I said, itself is a very it's an area on its own actually. So people have seen a lot of applications of graphs. when we are looking at even maybe the computer networks, if you want to study, or if you want to study the social network, also this graph theory is going to be useful, right? So there are many applications of graph theory, but from where it all started actually. So it all started with a good story about a good story about a problem called the Seven Bridges of Königsberg. Okay, so the Königsberg is a city in Russia actually. At present, the name is Kaliningrad. Okay, so you can have a look at it in the Google, search for Seven Bridges of Königsberg. You will come to know about it. So in 1730s, there was a problem in Königsberg, which was actually proposed by one of the, I think, the administrative mayor of this city, Königsberg city. So he asked actually. So there is a Pregel River. So this is the Pregel River, right? So this blue portion is the Pregel River, and there is a landmass like which is something like an island, and there is a landmass B, landmass C, and landmass D. Okay, so the question is like you have to start from one of the landmasses and then go through the bridges. So there are some bridges. So if you see that these things, there are 7 bridges actually. So this is 4, 5, 6, and 7. So it connects the land masses across the river actually, right? So there are 7 bridges that is connecting A, B, C, and D through the river Pregel. So his question was like you need to start from one landmass. Maybe if for example, if you take B, you need to go through. So you need to go through every edge. Okay, so every edge only once, and then you need to come back to the same place where you started with. Okay, so do we have such a solution, right? So that was the question that was asked by Königsberg, not Königsberg, the mayor of Königsberg actually, right? So people were like looking into all kinds of solutions. They were starting with A, starting with B, starting with C, and starting with D, but they were not able to. So they were not able to find a solution actually. And so it required the skill of Euler. So he is one of the greatest mathematicians. In 1736, he solved by telling that there is no solution for this. Okay, so from whichever place, from whichever landmass you start with, you will not be able to reach the same place again just by going through all the edge exactly once. You will not be able to do it. That is what he told, and for that he did a kind of an abstract study. How did he abstract this problem out? So he took this kind of a graph for it actually. So that time it was not called as a graph, but at a later point of time we started calling that as a graph. So this is abstract model. So all the land masses he chose like a node actually. So C, A is a node, B is a node, and D is a node, and all the bridges that you are having are all connected like from A to B. There are 2 bridges, right? So this is the first bridge, the second bridge, and then you have for A to C also we have 2 bridges. So that's why we have like this, and then C is connected with this bridge to D, and B is connected with this bridge to D, and A is also connected with this bridge to D, right? So you have this graph, and then he showed that if I have such a kind of a graph, and if one of the node is having an odd degree means the number of edges that is coming out from a node. Okay, So if you see the degree with for A, if you consider the node A, the degree is what? It is 1, 2, 3, 4, and 5, right? So it's an odd degree, right? So he showed by a mathematical proof, if there is one node in the graph which is of odd degree, then we will not be able to produce such a path. So that path that I said, you start from one place and you go through all the edges exactly once and then come back to the same place. That path is called as an Eulerian path. It is named on his name actually. So that is called as Eulerian path. So that we will be looking at again when we define what do you mean by path. Okay. So I'm just trying to give a motivation about the history of the evolution of the graph theory. Okay. So this path is called as an Eulerian path because Euler found this actually in 1736, way back in 1736. And that was the birth of graph theory. So why is it called as a theory? Because it is an abstract model. So he is building a graph which is an abstract model of this instance, right? So instance is here, there is land masses A, B, C, and D, which he is denoting it as the nodes. And the bridges, he is denoting it as the edges between the nodes. And he is able to study, in general, if a graph is having 1 degree which is of odd degree, then you will not be able to get such a path. That is called as the Eulerian path. Okay, so that proof, we are not going into that proof. You can have a look at it. It's a very simple proof actually. So the intuition is like if you want to go to if you want to reach a city, right? So then you need to go through an edge, right? And if you have to come outside of the city, means you need to come out of it, right? So anyway, you need to have even number of edges connected to it. If there is only one edge going to it, and you will not be able to come out of that edge, out of that node, sorry, right? So that is an intuition behind it. So you need to have even degree for all the nodes. So then only you will be able to get such a Eulerian path. So that you can look into in basic graph theory notes for the proof. We are not going into the detailed proof of this. Okay, so but you need to know about this. Okay, right. So let's explain it in a different way. When I define what do you mean by a path, we have not defined the path. What do you mean by path in a formal way, right? So, but this is the birth of the graph theory way back in 1736, and after that there was a lot of research going on, and still even after 260, 70 years, people are still working on this graph because there is a lot of applications that is there for graph theory actually, right? So let us define the graph. What do you mean by a graph in a very abstract way? So if we want to study about a group of actors, right? So this we started with the quote in the previous class, right, by a sociologist. So he told, if I want to study about the group of actors, then I need to study about their network, not the actors as such. So the connection is between the nodes. That is the connectivity. That is the one which is more important than the actor themselves. Okay. So you need to look at the graph. So how are you going to define a graph? A graph is nothing but it is represented as G is equal to V comma E, right? So G is equal to V comma E. And what is V here? V is a set of all nodes, or sometimes we call it as vertices, and E is a set of all edges, or sometimes we call it as links. Okay, so V is a set of all nodes and E is a set of all edges. So you can represent a graph just by defining what are the nodes in that graph and what are the edges in the graph. So if you can specify this, you already have a graph in front of you. Okay, So, and then the two parameters that will be helpful to describe the graph are the number of vertices. That is, we call it as the number of vertices, right? So that is denoted as like this, the cardinality of V. V is a set of all nodes, right? So you know how to represent the cardinality of a set, right? So this is the number of vertices, which is n. And then the number of edges will be denoted as m. So there are m edges and there are n vertices. So these are the two parameters that we will be using if we are defining a graph. Okay, right. And what is the beauty of the graph is, because it is an abstract thing, that node can be anything. So that node can be computers like this, or it can be some of the actors who have played in some of the Hollywood films, right? So these are the actors who have played in some of the Hollywood films, and the edges represent which film they were doing together, right? So these are the edges, right? And then it can be based upon the chemical molecules also. Some biomolecules are chemical molecules also, right? So you will be connecting those components in which we are having some kind of interaction between them, right? So some reactions between them, right? So all these are separate, different graphs. But what we represent as in the graph is nothing but an abstract node. That's all. So that node can represent any of these things. That is the beauty of abstraction. So graph is an abstraction. That's very important. Okay. So different networks, but it is the same graph. So there are different networks, but the graph is the same. So graph is an abstraction, right? So when we are talking about graph, we are talking about something which is abstract. We are not going into the specificity. Okay. So if I say that so 2 and 3 are connected, and 2 and 3 are some cities, right? So 2 and 3 are connected. So from the city 2, you can go to city 3. I am not going to describe whether it is a surface kind of a travel connected by a surface travel, or by a water like through a ship you go, or is it through a train only, or is it through flight? No, we are not going into the specifics of that, whether they are connected or not. So our concentration is on the connectivity. That is our important thing. Okay. So graph theory is about connectivity, is a study of connectivity. Okay. So different types of graphs are there, and different types of different characteristics of those graphs are there according to its connectivity. That's what we will be looking at when we are dealing with the graph theory, and even in the social network also. Okay. And these graphs generally, whatever the graphs that we have seen as of now is an undirected graph. It means the edges doesn't have any direction. Okay. So those are called as undirected graphs. There might be some occasions in which the edge have to be directed. So for example, if you are looking at the Facebook graph, right? The Facebook friends as a graph, right? So let me take 3 as a Facebook user, and 1 is also Facebook user, 2 and 4, right? So what does that mean whether 3 and 2 are connected together? Means they 2 are friends. 3 and 2 are friends. Means if 2 is a friend of 3, then it means that 3 is also a friend of 2, right? So it is a symmetric relation actually. So in the Facebook friendship, it's a symmetric relation, but that is not the case with the Twitter, right? So in Twitter, it's so I might be following someone, but he might not be following me, right? So so that is not a symmetric relation, right? So if I'm talking about a Twitter graph, then I have to look into a directed edge, because that makes sense. But in a Facebook graph, having a direction doesn't make sense, because we are already having both the ways. The friends means it is reciprocal. It's like a symmetric relation, right? So in some cases, we have to look into an undirected edges So it will be an undirected graph. In some of the cases, you may have to look into directed graph, for example, the Twitter networks. Okay, right. So so other parameters that we can look into when we are considering a graph is the degree of a vertex. So which we have already seen informally. The degree of vertex is nothing but the number of edges incident on a vertex. Okay. So suppose I take a graph something like this. Some random graph I'm taking, right? So and suppose I want to find the find the degree of this vertex, right? So then I can see that this is connected with 1. So one edge is going out of this V, second edge, this is a third edge, and this is a fourth edge. So the degree of V is equal to 4. Right? So likewise, I can find the degree of this vertex. So suppose I name this as V prime. I can find it like, so this is one edge, second edge, and this is the third edge, which is going out of it. So D of V prime is equal to 3. So like that, I can find all the degrees of the vertex, and that is called as a degree of a vertex, right? So for a graph, if there are n vertices are there, for every vertex, we can find what is the degree of that vertex. And then we can also talk about average degree of a node, so that we will represent it as degree of a node. Okay, so that is represented as like you sum up all the degrees, that is ki. For every degree you are summing up the degree, right? Ki is nothing but the degree of the ith vertex. Okay, and you sum up and divide it by n. So that's the average, right? So you have to sum up all the degrees and then divide it by n, and that is the average degree. Okay, so that is always denoted in our course by this. Okay, so this is for the undirected graph. If you are talking about an undirected graph, this is the case. But if you are talking about the degree for a directed graph, because every edge is having a direction in it, then you need to talk about in degree and out degree. You need to talk about this. In degree means the edges which are coming towards that node, how many edges are coming towards that node, and how many edges are going out of that node, right? So both the things you can talk about. If you are talking about an undirected graph, there is no in and out, because all the edges are having both directions there, right? So it doesn't make sense when we are talking about in and out in an undirected graph. But if it is a directed graph, it makes sense to talk about an in degree and an out degree. Okay, so you can now talk about the average in degree and then average out degree also. But the number of like the average in degree and the average out degree will be always the same. So that I am not going to prove it. You can easily find it. You can easily convince yourself, right? So this is the concept behind the degree and the average degree. Okay. Now let's see some of the networks that we will be interested in the social network. So what I want to do here is I'm trying to explain the basic graph theory concepts, and then at the same time I'm trying to introduce the networks that we will be studying, and so that I can compare and contrast and then tell what are the things that will be different from the basic graph theory concepts. Okay, so with the known thing, right? So the graph theory, you would be able to visualize it intuitively, and so that you will be able to compare with the networks that we are going to study, this large network that we are going to study, and then you can see what makes this network different from the basic graph theory. Okay, so let's see some of the networks that we will be looking at in this course. Okay, so until this point, do you have any clarifications?
Sir, I have a doubt in chat box.
Yeah, yeah,
I
tell
have
me.
written. Sir, I have written it in chat.
Okay, okay. Let me go back. Like two different scenarios can have a same graph, but can two different graphs represent same scenario? Yeah, that's quite possible. Yes, it is possible. It is possible. All things are possible actually. It's a many to many relation. Yeah.
Sir, how same scenario can be represented by two graphs? I mean,
No, it is like, see, so the scenario means what I'm talking about is, see, suppose I'm talking about the node as a Facebook user and the node as maybe another maybe YouTube user, right? So it can be different, right? But there might be the same graph which is representing both the things, but it is a so for example, I had also given this here, right? So let me go back to that slide. Yeah, here. So these are two different scenarios. A and B are two different scenarios where the node is representing a computer, and here in B the nodes are represented as actors, right? So it is two different scenarios, but you are having the same graph. This is one example.
yes, sir. There are two different scenarios, and one graph can be, but one scenario, two graphs are possible or not?
One scenario, yeah, you can see in some ways you can also look into a directed graph as an undirected graph in some cases. So you will be having the same kind of a graph, but at some point of time you might be looking at only the undirected version of the directed graph. So you can have the same scenario, but when you are looking at the graph, you will be looking at different kinds of things like the directed or the undirected version, or I will be looking at the edges as multiple edges also. So I have not defined the multi edges as of now. So
Okay.
everything is possible actually. Yeah.
Yeah, okay. Okay,
It
sir.
is according to the scenario. Yeah, it is according to the scenario. So whatever the problem is at your hand, so it is best described according to the problem that you are having. Okay.
Okay, sir. Yes, sir.
Yeah.
Thank you.
Yeah. So any other questions until this point? Okay, fine. So let me continue then. So we have seen the degree of vertices, like then we are going to look at some of the networks that we will be interested. So this picture is taken from Barabasi's book. You can have a look at it, and he has also described it well in the book about the various kinds of networks that you can look into when we are looking at the social network. Right. So the first network is about the internet. So here we are looking at the nodes as the routers and the links as the internet connections. And here it is, we are taking the undirected version of it, right? And then the number of nodes is some like 192,000 nodes, and links are like almost like 3 to 4 times of the number of nodes. Okay. So, and the average degree is 6.34, right? See, when the graph becomes large, see, when you are looking at a basic graph theory, what you are looking at is maybe 10 nodes or maybe 20 nodes or maybe 50 nodes or something like that, right? So you will be able to visualize the graph. You will be able to look into the graph, and then you will be able to find the different kinds of characteristics of the graph. But when the graph is so huge, you will not be able to look at the graph in the wholesome manner actually, because there are a lot of nodes and a lot of edges might be there. So the best way of describing it is through the number of nodes and the number of links, and give the average degree, and that will give you some kind of an impression about how this graph is how the graph is existing, right? So that is what you will be able to get using this kind of description. Okay, so let's first concentrate on only these three parameters. When we go beyond this chapter, we will be able to explain more and more parameters which we'll be looking at, more important nodes, more influential nodes, more nodes which are giving the connectivity measure. So like that, we will be looking at different kinds of characteristics of this large networks. Okay, so internet can be looked upon as one of the network. So that is having like average degree as 6.34. Okay, so this average degree is a very, very important figure. So that will tell you about the graph, whether it is a dense graph or whether it is a sparse graph, or whether it is something like in between kind of a type. Okay, and then what we can look into is the www, that is www, right? And the nodes here are the web pages. So the internet, we are looking at the nodes as a routers, but in www we will be looking at the web pages, where it is going to, which web page it is going to. And of course the links are the edges. So from which page to which page you are linking, that is the edge that you are talking about. And here it is a directed one, because here the link might be present in one web page to another web page, but that web page will not be having the same link going back to the same web page where it came to, right? So it has to be directed then, right? So the number of nodes over here for this, so this network was taken, I think maybe 10 to 15 years back or so, when Barabasi was writing his book. So so when we take the network presently in 2020, it might be 2021. I think now it is 2021. So it will be completely different. It should be definitely more than this actually, right? The number of nodes would have increased by now, right? So when we are considering the www, so I say that it is www, it is www. Okay, so don't get irritated by that. So this is one example in a lighter fashion. I'm telling you, this is one example in which if you, so this is an abbreviation, right? So www is an abbreviation. So naturally, why will you have an abbreviation? So suppose you want to tell some big word, you want to tell it in a simple way, right? So that is the beauty of having an abbreviation, right? But if you want to spell out www, then that spelling itself is more than World Wide Web, right? So I can say World Wide Web, which is shorter than telling www. So people call it as www. That's all. So you don't have to tell the completely www. So you can easily say that www. So that is one on the lighter version. So when I say that www, it is www. Okay. So when I'm considering the www network, I'm seeing that the average of this network is 4.60. Okay. So see, when I'm the number of nodes might have increased, the number of links also might have increased, but the average degree might not change that much in any way, in any case. Okay, the average degree might not change much. So that is the beauty of looking at the degree, the average degree of the nodes. Okay, and likewise, if I'm considering the power grids, okay, so we looked at the power grids as one of the case study when we looked at this electricity failure in the eastern part of US and Canada, right? So that network, if I take the nodes, will be the power plants or the transformers, and the cables or the links between them, and it is going to be undirected because there is no direction over it, right? And here the number of nodes is like 4,941, and the number of links is also not that huge actually, right? It's just maybe 1.2 or 1.3 times of that. So then you have the average degree is quite less, that is 2.67. Likewise, I can go to the other networks also. One of the important network which is completely different from the previous ones is the actor network. The actor network, if you see, actor network is nothing but the nodes are actors, which can have actors and actresses also. So now we call them commonly as actors, right? And the links are like co-acting. What do you mean by co-acting? It's like, so they have acted in the same play, right? So if the actors have acted in the same flame, then you will have a edge between them. So that network will be an undirected network, right? And now you see the number of nodes is like 702,000 approximately, and then you have like so this many nodes are there, right? So this is like almost like maybe 40 times or something like that, right? So and then you see the degree of the network. The degree of the network is like 83.7, right? So then that means for every actor, so he has acted with almost like 83 other actors, right? So then this network is somewhat different from the other networks because the average degree itself is so huge, right? Like, so let's keep that. And the other network that we can talk about is another one is a citation network. Especially in the research field, we can talk about the citation network. Here, the citation is nothing but the notes are papers, and the links are nothing but the citation. So if a paper one has cited about the another paper, then you will have a directed edge. So here the citation cannot be back and forth, right? So it is not possible at all in citation, right? So at one point of time, in the 1977, one paper would have come, and 1990 some paper would have come. So 1990 would have cited the 1977, but 1977 cannot cite the 1990, right? So the other way is not making sense at all. So it is going to be a directed graph. It cannot be an undirected graph. So in this case, you see that the number of nodes is like this, and this is like almost 10 times the number of nodes, and you have like the degrees also like maybe 10.43. So which is not that huge like the actor network, but still it is much larger than the internet, www, and power degree, power grid, and such kind of things. And if we see the email network is one of the least degrees, like 1.81, which is very very small average degree. So right, so this is the network that you are talking about. So another important point that you need to look into when you are looking at this kind of network is, in the basic graph theory, the graph which is in front of you is well defined, and the number of nodes is not going to change, and the number of vertices is not going to change. It is going to be same, and a priori you will be able to know about how many edges are there and how many vertices are there. But in a network that we are going to consider, the number of nodes may not be one specific number, and the number of edges may not be one specific number, because when we are considering the internet, the routers might come and go. The network sometimes fails, so the edges may not be there at all. In www also, the links might change. So one time you will be able to access one page, another time you will not be able to access that page at all. So it is completely independent of, so you don't have any control on that, right? And even the power grid, it is the same. Even the mobile network, it is the same. Email, it is the same, right? So you might be having an email address now, but when you pass out from LNMIT, you might not be having that same email address. So that might be deleted from the domain, right? So from LNMIT domain. So what we are talking about, a network which is completely dynamic in nature, right? So that is not the case when we are considering a basic graph theory. In basic graph theory, the graph is already given, it's almost fixed for you, right? So the number of nodes is there, number of edges is there, and it is not going to change with respect to time. But here it is having temporal aspects and spatial aspects. So it might change according to the situation, right? So that is what you need to keep it in mind when we are doing the social network studies. So even the network science, you need to look into the network where the number of nodes is not fixed and the number of edges is also not fixed. But the network will give you some kind of a picture about how it is through this average degree and the number of nodes and the number of links. Through these three parameters, you will be able to try to guess what kind of network it is. Okay, so that is the main point that you need to keep it in your mind. Okay, so until this point, any doubt? Okay, so let me continue. There are no questions, so I presume that you have understood. So let me go back. Right. Yeah. So how will you represent a graph? So that's called as a graph representation. So there are exactly two popular ways of representing. One is called as the adjacency matrix. Adjacency matrix, which is an n cross n matrix. So in which, right? So suppose you have 4 nodes. So here is the graph. You have 4 nodes. 1, 2, 3, and 4 nodes are there, and edges are also given over there. So suppose you want to represent this graph, I can represent using Aij, which is like, so these are the nodes like 1, 2, 3, and 4. 1, 2, 3, and 4, right? So now 1 and 1 are not connected by any edge, so I will put 0 over here. So unless you have a loop here, it won't be considered as 1 and 1 are connected. Anyway, you are at 1, so you don't have to get connected at all, right? So we consider that as 0. And then 1 and 2 are connected with each other, right? So like this. So then you will put 1 over there. So if the pair of nodes are connected with each other, then I will put 1. If the pair of nodes are not connected, then I will put 0. So 1 and 4 are not connected. So 1 and 4, 0 is there, right? So likewise, 4, 1 is also 0, right? So because it is a undirected graph and it's a symmetric relation. So if 1 and 4 are not connected and 4 and 1 are also not connected. If 1 and 2 is connected, 2 and 1 is also connected, right? So likewise, you will have this graph, and this is symmetrical with respect to the main diagonal. Okay, right. So this is for the undirected version. This is called as the adjacency matrix, which is always of n cross n matrix, where n represents the number of nodes. Okay, and then if the graph is a directed graph, then I would be looking into the direction also. Now, if I take the node 1, 1 is connected to 2, right? So if I take 1, 2, 3, and 4, and this is actually 1, 2, 3, and 4, right? So 1 and 1 are 0, right? And then okay, so they are taking like it is 2, 1. I mean, so you need to take it from the column actually. So 1, 2. 1, 2 is 1 actually. So 1 to 2 is there. Likewise, I have 3 to 1, right? So 3 to 1, right? So it is actually it is represented completely differently. So it's ulta, right? So 1, 3 is connected, right? And likewise, you have 3 to 2 is there. So 2, 3 will be connected. So 2, 3 is connected. And then 2 to 4, you have an edge. So it will be 4, 2. 4, 2 is connected. Okay. So anyway, if you are finding this way, you need to be compatible with all the other pair of nodes. That's all, right? So you can represent by an adjacency matrix, either a directed graph or an undirected graph. So in the case of an undirected graph, the if Aij is equal to 1, then Aji is also equal to 1, right? So Aij is equal to Aji, and Aii will be always 0, right? And in the case of the directed graph, right? So Aij need not be equal to Aji, and Aii will be always 0, right? So that is the important thing, right? And the number of links that you get, number of links. So L is nothing but the number of links. So the number of links in a graph is nothing but you sum up all the entries, right? So Aij, you will be looking at all the entries, right? You sum up all the entries over there, and then you divide it by 2, you will get the number of links. So in this case, if I want to look at the number of edges, how many edges will be there, I will be summing up 1 plus 1, 2, 2 plus 3, 5, 5 plus 2, 7, and 7 plus 1, 8, right? So 8 is my number, and divided by 2, right? And that is equal to 4. So we have number of edges as 4, right? So in general, what you can do is, if you sum up all the Aij entries and then divide it by 2, you will get the number of links. Likewise, here you need to consider in a directed graph, you don't have to consider by 2, because in this case, in the undirected graph, you are taking 1 for each of these cases, 1, 2 also and 2, 1 also, right? So you need to divide it by 2. But in the case of the directed graph, you are for every edge you are counting it as only once, right? So you don't have to divide it by 2. You just sum up all the entries in the directed graph, like 1 plus 1 plus 1 plus 1. So there are only 4 ones. How many ones are there? That will be the number of edges. Okay. So that is one point that you can keep it in your mind. Right. So the next important thing is about the degree distribution of a graph, which is very important when we are looking at the dynamic networks that I was talking about. So in the case of the network that we are talking about right now, so I said that the number of nodes might come, the number of nodes might go, the number of edges might come, and the number of the edges might go also, right? So the number of edges might increase or decrease, the number of vertices might increase or decrease. It will change dynamically, right? So when I want to represent and give some picture about how this graph looks like, so we had seen that there are 3 parameters that you can say, the number of nodes. You can give something like an approximate kind of a figure, like so B is equal to so and so 10,000, and N is equal to maybe around 50,000, and then the average degree is maybe 6, something like that. If we give, it gives us some kind of a representation. And if we want more information, you can also give something like a degree distribution. The degree distribution of a graph is nothing but how the degrees are distributed with respect to the vertices, right? So here, when I'm talking about the degree distribution, so I'm considering that pk. What is this pk is? Pk is the probability that a randomly selected node in the network has degree k. Okay, so I take the degree as k. Okay, I'm fixing the degree as k. Now I'm seeing how many nodes are there having the degree k, and that is denoted as nk. Okay, and then divided by n, that gives a probability, right? So if I want to find the node of if I want to find the probability of a node having a 2, I need to find the number of nodes having the degree 2, and then divide it by the number of nodes in the graph. Then that will give rise to the number pk. So pk is nothing but the probability that a randomly selected node in the network will have the degree k, right? And then so the number of degree k nodes then can be obtained from the degree distribution. So if you have pk, then I will be able to get nk just by multiplying the number of nodes into pk, because pk is something like a normalization, right? So when I'm considering the probability. I'm just trying to normalize it using the number of nodes that I have, right? So when I multiply with capital N, then I will be able to get back the number of nodes which is having the k degree, right? And then I can also find the average degree of the network just by getting the pKs and then multiplying with the k. What is k? K is a degree, right? If I want to find the number of nodes of degree k, nk is equal to n into pk, right? So then if I want to find the number of the average degree, then I can just multiply the pk, which is already normalized. Pk is nothing but pk is nothing but the nk divided by n. So you multiply with the k, where k is the degree, and then you sum up for all such k's where k is from 0 to infinity. That will give the average degree, right? So this you can easily see. So I'm not going to describe it. It's a very basic fundamental thing. You can easily prove it actually, right? So the beauty of the degree distribution is the degree distribution tells you the fact about the probability. It also gives a number of nodes which is of degree k, and then it also gives the average degree of the node in a straightforward fashion. And this degree distribution also gives some kind of a feel about the plot that you will be having. So according to the distribution, the probability distribution, you can apply some of the formulas that you will be knowing from the probability distribution that you would have studied in statistics and such kind of things. So it gives a much better idea about how the degrees are varying within a network. Okay. So for example, if I look at the Facebook degree distribution, this is how it looks like. So on the x-axis is a fraction of the nodes, and this is the degrees. So the degree is increasing on the x-axis, and this is nothing but a fraction. Okay. So if you see that, then I'm talking about the node which is having very less degree. I'm seeing there are many such nodes. So that means there are many nodes having less degree. So in Facebook, you might have seen there are many people who are not having much of connectivity, but at the same time, you would have seen there are few nodes having very large degree, right? So both the things are coming together. So users with lots of friends is so less, right? And users with minimum friends is huge, and that is called as a power law distribution. Okay, so this power law distribution gives you more and more idea about how the graph, which is very huge, is going to be visualized by you. So this gives us, so in addition to the number of nodes, the number of edges, and the average degree that you have, the distribution also gives you much more information about how the graph looks like, how the network looks like. Okay, so this we will be seeing in many of the social network analysis, social network graphs. So there are many users with the minimum friends, okay, but there are a few users who are having many friends. So this is something like so for example, if you take the Twitter, right? So even you can take Facebook also. Like if you take Narendra Modi or Amitabh Bachchan or maybe other popular figures, right? So they will be having many friends actually, maybe millions and maybe thousands of friends they will be having. But there are many people, a normal person, who will be having like maybe 10, 20, 30, 40, 50, maybe has some 100 friends. That's all, right? So there will be many people. So that that many people will be having very less friends, but there will be few people who are having very, very large friends. So generally, this kind of a power law distribution will have a long tail actually. Okay, so let's come back to this again when we look into the network in the course of this course. Okay, right. So maybe so I will give you some few minutes, maybe if you have any questions or so until this point. I'll go back to the chat window. So if you have any questions, please let me know. Right. Okay. So there seems to be no doubt. So let me continue. So there may be few occasions in which you might have to look into the graph as a weighted graph also. So what do you mean by a weighted graph is you are giving some weights for its edges. So that is called as a weighted graph. So for example, if I'm considering a simple graph like this, I can put some weight like maybe 2 or 3 or 5, 1, 2 like that. So I'm just giving some weightage. So what does this weightage will represent for every edge? It might represent the cost of going from one node to another node, or it might be representing the distance between the two nodes, right? So for example, if this is like maybe Jaipur and this is Udaipur, and if I say that it is 2, then maybe it might be something like it might be something like it takes 2 hours to go from Jaipur to Udaipur. I'm just giving some kind of an example. That's all, right? So it might represent 2 hours, or maybe it is 200 kilometers or something like that, right? So it can represent some number, right? So that will make sense in some of the situations when we are considering a graph which needs to represent this parameter also. So in that cases, we will be talking about weighted graph. A graph with weights associated with the edges is called as a weighted graph. Okay. So in a graph, we assume that all edges have equal weights. In a normal graph without weight, we are actually considering that every edge is having weight 1. But in the case of the weighted graph, it may not be only 1, it can be any other number, right? Right. So for example, I had already told you some example, but some edges will be used more than other edges. So for example, the rail network, right? In the rail network, some of the edges might be used many times, and some of the edges that is a rail network may not be used many times, right? So you may have to give importance to some of the edges more than the other edges. So in that way, you may have to give some weight for that, right? And if you are considering a weighted graph, the adjacency matrix takes care of the weight. So Aij will be now equal to Wij. So instead of just 1, if the I and j so are connected, I said that Aij will be 1, right? Instead of that, we will be putting the weight W. So where W is a number, okay, so real number. So if the graph of this is so like 1, 2, 3, 4, there are 4 nodes. So 1, 2, 3, 4. I will say that 1 and 3, right? 1 and 3 is, in a normal graph will be 1, right? In this case, it will be 2, because that is a weight, right? And then this is a graph which is like if I'm considering this. Okay, so there are 4 nodes. I need to represent that. I have not represented it. So this is 1, this is 2, and this is 4, right? So it means then 1 and 4. So this is 1 and 4. So 1 and 4 is 2. So like that you can fill it up, okay? So the adjacency matrix will take care of the weights. And now coming to the important point of the network. So it is not about, I had said that when you are considering the network, it is not about the nodes you are considering, you are talking about the connectivity. So when you are talking about the connectivity of the network, it means that the value of the network is proportional to the square of the number of nodes. Means the value of the network is more than the number of nodes actually. So exactly speaking, it is a square of the number of nodes. So for example, if I have a network, what will be the maximum and the minimum number of edges a network can have? So suppose there are n vertices, what will be the maximum number of edges it can have? So there are n vertices, right? So what will be the maximum number of edges it can have? Yes? Are you all there? Yeah, n into n minus 1 by 2. It's of order of n square, right? So when the n increases linearly, the value of the network, that is the connectivity of the network, it increases the square of that number actually, right? So the value increases square of the number of nodes. That is very important, right? So that is why whenever a cellular network is going to build up, right? So they want more and more people to join there. So why is it so? As and when many people join their network, for example, the Reliance Jio or the Airtel or something like that, so their value of that network will increase the square of that. So what they have to spend is only to add the node. So they may have to spend some money for adding one node, but the increase in their profit will be like square of that the number of people who are joining in their network. Okay, so that is very important. So you need to consider that. So that is what is explaining here. So that is called as a Metcalfe's law. Okay, so more individuals use a network, the more valuable it becomes. So for example, the WWW network, the cellular network, and so on, right? So people want more and more people to more and more mobile users to join their network, so as to increase their revenue in the squared way, right? So what they have to spend might be minimal, but with that minimum, you will be able to get square of that revenue. So of the number of orders of the users who are using that network, right? So the cost associated with the network increases linearly with the number of nodes, but the value will be square of it, and that is very important to note. And there are various types of networks also you can look into. And here in this course, we will be looking at various types of networks also. Well, one way of looking at the network is called as a bipartite network. What do you mean by a bipartite network? Is it is a network whose nodes can be divided into two disjoint sets U and V, such that each link that connects a U node to a V node. So every link will be connecting between one node to another node. So like this. So you have the node set U and the node set V. So here are the nodes of V, and here are the nodes of U, right? And every edge is between them, between U and V, rather than within U or within V. So there are no edges within you here like this or here like this, right? So there are no edges like this. So that is very important. So it is a particular case of a network in which I can partition the vertex set into two, u and v, and in such a way that every edge of that graph is joining one node from u and another node in v. Okay, so that is the important thing that you need to keep it in your mind. Right. So we can generate two projections for each bipartite graph. Well, what are the things? The first projection connects two U nodes by a link if they are linked to the same V node in the bipartite representation. And then the second projection connects the V nodes by a link if they connect to the same U node. Right. So this is a projection of V. I'm talking about V. So here we are talking about the projection of U. So let us take the simple one, which is the projection of V, which is very simple to understand. So here A and B are connected. Why is it so? So A is connected to 3. Okay, no, not 3. So A is connected to 2 and B is also connected to 2, right? So if A and B are connected to a common node, then I will be having an edge. So that is called as a projection of B. Okay, and likewise, B is connected to C because so this is connected to 5 and C is also connected to 5. So B and C is connected to each other, and likewise B and D is also connected to each other because B and D is also using the 5. It is connected to each other, and likewise C and D is also connected because C is connected here and D is also connected here, and A is not connected to C and A is not connected to D because whatever the A is connected to, that is 1 and 2 and 3. So these two nodes are not connected to 1, 2 and 3, right? So this is the graph that will tell you like which are the vertices which are having common nodes between each other, right? So you will be able to go to B just by with one node, right? And so that is what it is. So if I want to go to C, I have to go through only B. That's what it says. If I want to go to C, I need to go to B and then from C. So if I want to travel from a city A to city C or city A to city D, I need to go through B. Then that means the node B becomes much more important. B becomes a more centralized kind of a node. So in the next few classes, we will be defining various kinds of centrality measures. What do you mean by centrality measure is it gives the importance of some of the nodes that you need to talk about. So here in this graph, the B becomes a very important node because if the B is not there, then A will not be connected to C, A will not be connected to D. So B is very important. But if I want to take out A, it doesn't affect the network because B, C and D are always connected with each other. So there is no problem. So A can be disconnected, but B should not be disconnected. So B is very important node in this network. So now this network is a very small network. So you are able to see whether B is important or C is important or D is important or A is important. But if the graph is huge, right? So what we are talking about is thousands of nodes and millions of nodes and like even millions of edges, right? So if that is the case, then when we are talking about this kind of the important nodes and central kind of nodes, then it is very difficult to find it, right? So you need to have some kind of an algorithm to find such a kind of nodes. And for that, we will be looking at various kinds of centrality measures, which we will be defining in the next class. Okay, so but before that, we have to define some more basic terms in the graph theory. We will be defining it in the next class. I will be stopping today's class with this, and I will be open to any questions that you want to ask me about any kind of clarification that you require until this point. Yeah. Okay, so let me go back to the chat window. What are some of the applications of bipartite graph? It's a very simple application is number of, so suppose LNMIT want to assign hostel rooms for the students, right? So one set of nodes is the students and another set of nodes is the hostel rooms. And then you will draw edges if that student is selecting this hostel room. That's all. It's a very simple kind of a bipartite graph, where one set of node is the set of all students and the other set of nodes is the set of all the hostel rooms. Yes, we will be sharing the recordings of the classes by this weekend, definitely. Classroom code of SNA. I'm not using Google Classroom, so I don't have any code. So we will be using Piazza for it. And the Google Meet links are already available in the Piazza also. You can go to the course information tab and then you can see the links. So for Tuesdays, there will be one link, and for Thursdays, there will be a link. So you can join using those links. Anyway, if you open the Google Meet webpage itself, it will be showing your class, I think. So any other questions you have?